All right. Before we start, are there any questions about what we did so far, or about how the class is going to go? Let me just turn on more lights. 1 second.
I have a quick question about the problem sets.
Yeah.
You said there's going to be 6 bi-weekly, I'm assuming.
Yeah.
When are we receiving the first one, and how should we submit them?
Well, you're going to receive it soon.
And then it'll be on CrowdMark, I assume, or something?
Yeah. Well, I'm not sure yet, but I think it will be on CrowdMark, and I think it will be better if people submitted typed assignments. So I'm proposing that people should LaTeX their assignments. I don't want to give the assignment right away because there's still people joining and leaving and so on. Okay, so far, wait, let me just see how many people are in the room yet. We're still not at 210. Any other questions? Okay. So, right. So last time we talked about this change of point of view, where in the Newtonian way, in the Newtonian formalism, you have a regular space. You have what we call a configuration space, and on that configuration space, you have a vector field, or at least it appears to be a vector field, which is called the force field. And then you use that vector field to write a second order differential equation. And that second differential equation is Newton's law. It's right here. It's just telling you that the second derivative of your trajectory, you're looking for a trajectory whose second derivative at any time coincides with the value of the force field at that position. And if the force field depends on time, it would have to be at that time as well. So at every moment in time, the force is telling how the velocity should change. So the implications of that are that in order to know the future description of the motion, in order to know the trajectory, you need to specify the position and the velocity of your trajectory at a given time, and then you can figure out the rest. And there is something obviously kind of not straightforward about that. It's much more straightforward to solve first order ODEs. So the idea of the Hamiltonian formalism, which of the Hamiltonian formula, is to convert that second order equation into a first order equation. And so in order to do that, we need to double the number of variables, so that now we have x's and p's. P is just defined to be m times x dot, right? And then we obtain a system of first order equation. And this system can be interpreted as defining a vector field, right? So this system of equations is basically saying at any given position, this is what the velocity should be. At any given position in phase space, given x and p, the right-hand side gives you two quantities, which the derivative of x and p must be equal to. So you could think of that, if you think about what that is a vector field on the phase space, right? The right-hand side gives you the expression of the vector field. So at any given x and p, we can evaluate this. We get two quantities, and those are the two components of the vector. So in other words, from the Hamiltonian point of view, what we have is a phase space and a vector field. Okay, and the problem then becomes to given an initial condition, given an initial point in phase space, what is the future trajectory? And those have a name. They're called integral curves. So integral curves. Oh, what am I doing? I'm erasing things. Okay. So the integral curve, an integral curve is a curve. It's a map from the real line, the timeline, into the phase space, and it must satisfy the condition that its velocity, or its first derivative, is the Hamiltonian vector field. So, just roughly speaking, and summarizing everything so far, summary. In the Hamiltonian formalism, we have a phase space which has twice the number of variables, and we have a Hamiltonian vector field, V, which depends on the phase space. And the problem is to find trajectories, find integral curves of the vector field Vxp. So so this is okay. So there's a question which is, why, what is so good about the Hamiltonian formalism? Okay, so I want to answer that question today. But before I do that, I just want to explain a little bit more about how to solve the problem before we explain why this way of phrasing the problem is so much better. First, how to find these integral curves. Okay, so I just want to give some mathematical detail on this general problem of finding these integral curves. Okay, so this is a mathematical aside. Okay, so this is an aside on integrating vector fields. This is something that you would learn in a differential geometry class, but I'll just give a brief description of what, how we think about this. So, so let's start with some space, we normally call it a manifold. If you don't know what a manifold is, don't worry. It has coordinates x1 up to xn. Here, these could be x, p, y, z. It does not matter. I'm just using x because it's a typical name for a coordinate. So I'm not working on configuration space or phase space or anything in particular. I'm just working on a general space which has coordinates, n coordinates like this. a vector field can be written. So what is a vector field? It's just a tangent vector at each point, which varies smoothly. So how do we write that? Well, we want to write it in terms of the basis of vectors. So if we have coordinates x1 and x2, then we have unit vectors. We have this one, which is just the unit vector, but at every point. At every point, we put the unit vector pointing in the x1 direction. So this unit vector in the xi direction it has a name. It's called d by d xi. It's not the derivative of anything. It's just the derivative operator. The reason why we use this terminology, this notation, is because if you wanted to take the derivative of a function in this unit direction, you would just apply this. So this is good enough. This is a perfectly good way of representing that direction, because it tells you what you can do with that direction. You can differentiate a function in that direction. Okay, so I drew one of them. There's also d by d x2, which is mapping up like this. So this is d by d x2, and this is d by d x1. Okay, this is just notation, which I'm sure that you have seen other notations for this, namely like x hat, y hat, and so on. Okay, any questions about that so far? This just gives a basis. So we have a basis for all tangent spaces, which can be written like this: d by dx1, d by dxn. Any questions about this? I just needed a frame so that I can describe any arbitrary vector. It's going to be a linear combination of these. If you're confused by this, just ask. I'm sure there's many people who are confused.
Professor?
Yeah.
The coordinate, we're just working locally right now, right?
If you know what that means, good for you. Yes, the answer is yes. But the point is that I'm just using a coordinate system. So what Neo is asking is, are we working with a coordinate system? Yes, we're working in coordinates. But if you wanted to change coordinates, okay, the reason that this notation is very useful is because it tells you how to change coordinates. So for example, if x tilde 1 is a function of the other coordinates, if we change coordinates like this to a new set of coordinates, all right, so in a new set of coordinates, the new coordinates x1 tilde, x2 tilde, and so on, they depend in some complicated way on the previous coordinates, right? And then you might want to use the basis of the tangent space for these new coordinates, right? So the basis would be different. It would be d by dx tilde 1, and so on, up to d by dx tilde n. And so you might want to know, how do we change basis? How do I express this basis in terms of the other basis? Well, you learned this in multivariable calculus, right? So the idea is that d by dx tilde 1, let's say, would be dx I by d, dx tilde I by dx, oops, sorry, d by dx x1 tilde. So this calculation might be a little bit more difficult to do. So instead, you might you might do the reverse, let's say. The reverse would be easier. If you wanted to write d by dx1 in terms of the new basis, right, then you would write it as a sum of the derivatives x tilde I by dx1 d by dx tilde I. Okay, so the notation guides you using your knowledge of multivariable calculus. You know how to express the old basis in terms of the new basis whenever you change coordinates. So we're working in a coordinate system, but we're working in such a way that it should be clear how to change coordinates no matter what coordinate system you're interested in, okay? So this discussion here was just about what you should do in case you want to change coordinates. Okay, so let me just make that. Okay. So we have our basis for all the tangent spaces, and that means that so a vector field may be written as follows. So we just take V and we write it as V1 d by dx1 plus V2 d by dx2 all the way to Vn. Usually I won't write all of these coordinates, but just to begin, for the beginning, you need to understand what I'm writing. So this this thing is just n functions. All of these are smooth functions of the n variables, and they are giving me the components of the vector valued function. They're giving me the components of the vector field. Okay, so if V1 is really big, then the vector field will be pointing mostly in the one direction, and so on. Okay, so as long as the vector field is smooth, it can be described in terms of n smooth functions and so on. Okay, now through every point, so given, okay, so here's the key point. So a vector field gives rise to a flow, or sometimes called a dynamical system. It basically just means that, for every point, we can find the integral curve through that point, and that point will move. You could think of it as a time-dependent motion, and it follows the vector field. Okay, so if you wanted to describe, some kind of a system that undergoes a motion, all you need to do is give me a space with coordinates x1 up to xn, and give me these n functions, or one vector valued function. And as soon as you've given me that data, there's automatically going to be a flow whereby the particles, or any given particle, starts to move following the integral curves. So it's a simple way of providing a moving, a dynamical system, a system of data that undergoes a time evolution. Okay, so how does this work? Through every point. We have a unique maximal integral curve gamma on some time interval which goes from minus epsilon minus to epsilon plus, where epsilon plus minus are positive real numbers. So we don't know exactly what the time interval is in advance, but there is a maximum time interval satisfying the condition that first of all, gamma at the time 0 should be an initial point. So this is the initial value. And the second condition is that the derivative at any time of this curve, of this path, is the value of the vector field wherever the path happens to be at that time, like we said before. Okay, so why does this, why is what I just said true? Why does there exist this unique maximal integral curve? Why does this red curve, like for example, in this case, what could happen is that the vector field might be such that this red curve spirals in like this. Okay, and also if you go for negative time, it might do something like this. Okay, so this is an example which might be defined for all time. So the maximum interval of existence might be the entire real line. Or it could be that what happens is that you start moving, and if the vector field is growing very rapidly as you move to the right, what might happen is that the particle speeds up so quickly that within a few seconds, it already goes to infinity. And so it might be that after a certain time interval, it just stops, and we don't get a continuation because the particle has already gone to infinity. Okay, so but why? Why is this the case?
So in order, just explain that a little more. I'm not sure what you mean by after a small time it already goes to infinity.
Well, let's say that after 1 second it travels 10 units to the right, and after the next second it travels 100 units to the right, and the next second it travels 1,000 units to the right, and so on, right? So you might get a situation where the vector field is so big on the right. When you go 1,000 units, the vector field might be even larger and larger, and when you travel, it might be that the growth of the speed is so quick that it goes to infinity in finite time.
Thank you.
Okay, so in order to see that, you should try the vector field, which looks like this on R with coordinate x. We have vector field x d by dx versus x squared d by dx. Okay, so take a look at the difference between these two. Here, what we see is that if you're 20 units out, if you're 20 units away from 0, then the size of the vector field will be 20 units, right? So the size of the vector field grows the further you are from the origin. Okay, and here, on the other hand, it grows a lot faster. So if you're 10 units out, the vector field is 100 times larger. Okay, so it turns out that, and maybe I should put this on an assignment, that if you try to find the maximum interval for this one, you will be able to go for all time. It will take you infinitely long to go to infinity. But in this case, you get what's called a finite time singularity, which means that there's only a finite number of time, a finite amount of time, and this thing is already at infinity, and it does not, there is no continuation after a fixed time, which depends on your initial point. Okay, so, but in any case, the claim is that for some interval, you will be able to find a solution. You will be able to find a trajectory that that follows the vector field. Why? Why does this thing exist? Well, the reason is clear once we write it explicitly. So we write the equation explicitly. So we see that gamma of t, okay, gamma of t will be a curve inside an n-dimensional space, and so it will have n components. So this, I can write it as gamma 1 of t, gamma n of t. These are the n components of the curve, okay, because the curve is a curve in an n-dimensional space. Okay, and so if we write the equation star, what we'll see is that the time derivative of the first component is equal to what? Well, the vector field has n components, and it's the first component of the vector field that tells gamma 1 how to change. So what we need is v1. The second component of the path is affected by v2. And so on, until the nth component of the path is affected by the nth component of the vector field. Okay, but what does the vector field, what do the components of the vector field depend on? Well, we see that the first component, I'm sorry, I put them up, they should be down. So what do the first and second and so on components of the vector field, what do they depend on? They depend on the position in your space, right? So they depend on the values of x1 and xn, but those values are specified by what this path is. So the path has to be put in here, has to be plugged in. Gamma 1 of t, gamma 2 of t. All the components of the path will affect, the positioning of the path will affect what the value of the vector is. So that needs to be plugged in to v1. And the same thing goes for v2 and so on. Okay, so this is the system of equations that you really are trying to solve. Okay, the integral curve equations, these are the integral curve equations. Okay, they are basically saying that you need to find n functions of time. Okay, these are gamma 1 of t, gamma n of t, we need to solve for them given v. So given the vector field, we need to solve this system. So what is it? What kind of a system is this? Well, let me just change the dots for those that are not comfortable with that. It's d by dt. So this is real valued functions, 1 up to n. On the left, we have a single derivative On the right, we have some possibly nonlinear function of all of these functions. So this is a system of nonlinear first-order differential equations. It's a system of nonlinear. The reason they're nonlinear is because the right-hand side depends nonlinearly on the unknowns. The reason that they are ordinary is because there's only one variable, t, differential equations. Okay, and the most important and perhaps the only real theorem that you learn in a course on differential equations is that for any such system, there exists a unique solution with a maximal interval of definition. So the existence and uniqueness theorem for ODEs is the reason. So secretly, when you learn about solving systems of ODEs, nonlinear systems of first-order ODEs, what you are really learning to do is to flow a vector field along a trajectory. That's what you are learning to do. So if you, if you have a vector field on some space, it could be like a vector field on the Earth, like let's say the vector field determined by the air velocity. Wind is a vector field on the Earth, let's say, and if you wanted to know how that thing flows for a certain amount of time, what you are doing is solving a first-order system of ODEs. Any question about this?
So, like, these don't have to be nonlinear, though, right? Like, they could be linear in the end.
Well, I mean, it could be that V1, for example, only depends on, is a linear function of gamma 1 up to gamma n. That's possible. It could be, for example, the sum of those n components. But yeah, there's no reason in principle why the vector field should be linear. And in fact, if you're working on a general space, the meaning of linear is questionable. Like, there's no such thing as a linear vector field on the sphere, for example. The only space on which you can have a linear vector field is a vector space. So if your problem is not really happening on a vector space, it doesn't even have a meaning to say that the system of ODEs is linear. Okay?
Question?
Yeah.
And do we need to emphasize the fact that this is first order?
Well, the theorem that you proved is for first order ODEs.
Oh, okay, yeah.
That's the theorem.
And that's the
on the
advantage.
Other hand,
okay.
On the other hand, there is a trick, right, whereby you can take a higher order ODE and you can write it as a system of first order ODEs. So in the end, the order of the equation is not so important. What's more important is that it's nonlinear on the right-hand side. So you need a theorem to that effect. If it was linear, it would be easy to just write down the solution just analytically. We could just write down the solution. That's what we're going to do in a moment. But if it's nonlinear, you need a theorem to tell you that there is a solution. And you probably proved it in your class by using the contraction mapping theorem or something about I forget what they call it. Some Poincaré method, where you get it's a method of approximation. Okay, so what can you do with this? Let's just push it a little bit further and then go back to the physics. Okay, so the integral curve. So in other words, there exists a unique integral curve through every point. If we put all these together, all these curves, we get something quite interesting. Which you could call a global flow. Okay, and let me explain what that is. So what you do is you take the timeline, put it vertical like this, and then in the horizontal direction, we'll just have M, our initial space. So this has x1 up to xn coordinates. So I can't draw so many coordinates, but I'll just draw it as a single line. Okay, and the idea is that, okay, and then here I'll draw M again, but I won't draw a picture of it. Okay, and then let's take a look here. So at time equals 0, I could choose a point in M. That point is, I'll draw the space M as a, like this. So there's a point here. Okay, now there's this vector field on M. Okay, and I know that there exists an integral curve through this point for some interval of time. So we'll draw the domain of the curve on the left-hand side. So there will be some interval of time from minus epsilon minus to epsilon plus. There will be some open interval of time for which this curve is defined. So this, I'm drawing now the domain and the range of a map gamma of t, which has the initial condition gamma of 0 is equal to x. Okay, but the interesting thing is that I can do this for any point. So for example, if I picked another point, y, which is here, suppose, then there will be an interval for that value, and that will describe an integral curve through y. And so what you could do is you could assemble all these intervals all together, okay, and what you would get is a huge open set inside M cross R. Which is made up of the union of all the open intervals for each possible initial point. And each, for no matter what point it is, you're going to get a curve through it. Okay, and these curves will all be separate in the manifold because, you know, if they were to intersect, what that, you know, that would mean that the future trajectory and the previous, the you know, going backwards and forwards in time, you would have to follow the same vector field. So if you know, it's clear that for two different points, these curves will not intersect, because if they did intersect, then at that point, if we looked at the future or previous behavior of the integral curve through that point, it would be unique again. And so there's no way through uniqueness for these things to intersect. So what we get is a kind of a stream, like a water stream over the entire space M, which kind of looks like this. So what we get is we can assemble all of these together into one big map, which I'll call phi sub v. So we get phi sub v, which goes from m cross r to m, and it takes a point and a time to gamma of t, where gamma at 0 is equal to x is the integral curve beginning at x. This is the integral curve of v starting at x. Okay, now remember that I said that these intervals, they don't have to be the entire timeline. It might be that there's a limit where you cannot go any further in time than a certain, oh, I didn't draw that interval very nicely. This interval should go up to here. Okay, so what that means is that this map will not be defined on all of m cross r. It will be defined on some open set. This is an open set containing m cross 0. So that's the open set that I drew here, this shaded region. And this is called, this is the global flow. So this flow is phi sub v. And you can really think of it as, so if you're lucky, let me just make a note here. So if you're lucky, if we are lucky and u is all of m cross r, okay, so meaning that each integral curve is defined for all time in the real line. Okay, so if that happens to be the case, then for each t, we can consider phi sub v restricted to m at that particular time. So so this will be now a map that takes the initial values to the final values, and it will be an isomorphism from, or yeah, and let me just say that it's a map from m to itself, a smooth map from m to itself. And this, you could call it phi v at the time t. Okay, and the cool thing about this flow map is that it is compatible with addition of times. Okay, which means kind of, this is maybe not so surprising, that if you flow the vector field for a certain amount of time, let's say t1, and then you flow the same vector field for a time t2, then this will be the same thing as if you had flowed for the sum of the times. Okay, so this is not surprising because basically the idea is that you start at a point, you flow v for a certain amount of time, you get somewhere else, and then you continue flowing the same vector field for another time interval, t2. So of course you could have not stopped in the middle and you could have just gone the entire way.
Professor,
Yeah.
I have a quick question. For the interval of time on which the integral curve is defined,
Yes.
you know, of course, that on a compact manifold, you have a minimum sort of length that you can go for every point. But can you find a minimal length for any manifold that's maybe perhaps not compact?
No.
Okay, sounds good. I just want to check that.
Minimal length could be 0. It could be that the further you are out, you know, if the manifold is very large and you can travel right very far away, it might be that the further that you get, the less time is available for flowing until there's no limit, and so it just gets smaller and smaller and smaller. And so it, you know, no matter what epsilon of time you want to flow, maybe far enough away it will be less than that epsilon.
I see, that makes sense. I guess you can also construct it like a cone using some manifold with a problem.
What I suggest is that you try to do this exercise and then you'll have your answer.
Okay, thank you.
You're welcome. Okay, so because of this fact, it's often useful. So it's useful to write this flow, this time t flow, as in this way. It's like e to the tv. Okay, so this is not you shouldn't worry too much about the particular notation that's being used, but in other words, this is just a notation. It's not literally to be viewed as if you were plugging the vector field into the exponential function. That's not what it really means. It's the reason for this is because of the equation above. So that if e to the t1 v, e to the t2 v, this will be e to the t1 plus t2 v. Okay, so it satisfies the same law as the exponential function, and right. So sometimes you could call this the exponentiation of the vector field. So you'll sometimes hear people say things like that. So the exponential of a vector field is the flow. Or another way of thinking of it is that see these flows for time t, they give you motions of the manifold of the space M. They take the space M and they map it to itself. You could think of it as if it was like a rotation or some kind of a taking the points of M and moving them to a different location inside M. Okay, that's what this flow is doing. It's taking all the points and following the integral curves until you get different points. So what you see is that the vector field is kind of just pointing the way, right? It's not actually mapping the points anywhere. It's just giving you a direction and a magnitude in which the point wants to move. But then when you integrate that vector field, you get the actual motion of the points of M, right? So there are two things happening here. There's an infinitesimal motion. V is an infinitesimal motion. And phi of V is the actual motion. Okay, and these motions are called symmetries. I mean, we're going to see cases in which there are obviously symmetries. I mean, when I say that something is a symmetry, there's an implication that something is being preserved. So right now, we don't. I'm not claiming that anything is preserved under this motion, but you could think of it as if this is a map from the space to itself, and so it's like a rotation or a motion of some kind. It's something that you can understand as a symmetry, and we're going to make that more precise as we go along. Okay, so given a vector field, this is the main thing that you can do with it. You can produce a flow, which is a map from the manifold to itself, from the space to itself. And you get one of these maps for every time. It's just that you need to be careful about these intervals. If the time, it might be, for example, that time 1 is not available to you because some of these points may not have a maximum interval which includes time 1. It might be only time 1/2 or so on. And it might even be that the intervals, as you move in this direction, the intervals might be getting smaller and smaller and smaller. And so you might not have a global flow defined for all points for any amount of time. But anyway, the key point is just that vector fields integrate to flows. And these flows are motions of the space. They take points in the space to other points in the space, and they satisfy this nice additive law so that they behave like the exponential function. Okay, so is that I'm going to say one more thing about these flows before we take a break. But yeah, let me just say so there's another viewpoint. So, and this dichotomy of viewpoints is going to be true in classical mechanics and in quantum mechanics as well. So there are two ways of thinking of this flow. Okay, what I already described. So above, we think of it as a motion of points x in M are moved to phi t of x in M. So we think of it as a motion of points, elements in the space. The second point of view is that we could think of it in a more abstract way. We could say, how do we identify points? How do we tell someone, like if I had to tell someone which point am I starting with and which point am I ending with, what I would really tell them is the value of the coordinate functions, right? I would give them a certain set of numerical values of the functions, the coordinate functions. We can, and then I would say, well, the point at 1, 0 moves to 2, 0 or 2, 3, something like that. So it's more focused on functions on the space, the coordinate functions or some other functions on the space. So this is the second way of thinking, which is we can think of it as a motion. We may consider it we may consider the way this flow affects functions on M. So in other words, if I have a certain function on M, let's say if this is M, imagine that I have a function that looks like this. Okay, then maybe the flow is moving this way, and maybe what happens is that this function moves. I hope that's clear, right? So instead of thinking of the individual points moving, you could think of the entire function moving. Okay, now this is going to be very important. So later on, we're going to see they make a big deal out of this in physics. They call it the the Schrodinger versus the Heisenberg pictures, right? So in one picture, you think of the points as moving, and in the other picture, you forget about the points and you think of the functions on the space, and you think of how the functions are moving. So how are functions affected by smooth maps phi from M to M? Okay, so let me just, this is a little aside to explain the basics of how functions are affected. So a function on M is just, what it sounds like. It's a function of the n variables. So it's a map from the space into the real numbers, or it could be into the complex numbers. We'll see examples of that later, but most of the time it'll be the real numbers. The set or the vector space of all functions, of all smooth functions. Smooth function just means that you can differentiate it in infinitely many times. Smooth functions is called C infinity MR. So just the set of all functions. Okay, and now look at what happens. So if I have one of these motions, which is a map from M to M, and if I have a function on M, okay, then I can produce a new function on M by just composing phi with F. So this is phi composed with F. And this has a name. It's called phi upper star F. Or in other words, this is called the pullback of F by the map phi. Okay, so if the function f, right, like if the function, let's say this was m, and the graph of the function was like this, right? So maybe it has value 5 at the point 1. Well, I'll call these points x and y. So if the function has value 5 on the point x, right, and if the motion takes the point y to the point x, right? So imagine if this motion phi took y to x, then what you would see is that the pullback function, if I evaluate it at y, what would it do? At y, it would shift y to x first, and then it would evaluate the function at x. So the value of the pullback would be 5, but not at x, rather at y. Okay, so if you are moving, if the motion is taking one point to another, the pullback function evaluated at the initial point will be the value at the final point. So it's basically a way of dragging functions along these motions. So this drags the function back along the flow. That's why it's called a pullback. It's because it's going in the opposite direction. If the points move forward, then what happens is that the value of the function at the initial point, the value of the pullback at the initial point is really the original value at the final point. Okay, it's a little bit awkward to say it out loud, but hopefully you can just look at these diagrams and make sense of it. So this is how these maps affect the functions. So in other words, we get a map phi upper star, which takes a function on the manifold to another function on the manifold. So you can think of the flow, and we can actually think of it as doing this for every time and for each vector field. We get we get this is the effect that it has on functions. Okay. Okay, and yeah, and the last thing I want to say is that from this point of view, it actually the exponential formula actually makes sense, because the interesting thing is that a vector field doesn't really act on a point. A vector field doesn't take a point to another point. You need to integrate the vector field in order for it to act on points. But a vector field, it actually can act on a function because it can differentiate the function. So the nice thing about thinking about how the flow affects functions is that, V also acts on functions. For example, if I take V, then I can apply it to a function, and what would I get? Well, I would get just the obvious thing. I would get Vi df by dxi, sum from I is equal to 1 to n. So the vector field actually also defines a map from functions to functions. It just differentiates the function and produces another function. This is why we wanted the functions to be infinitely differentiable, because then we could differentiate it. I'll take your question in a second. So the cool thing is that yeah, so the nice thing is that if we take phi t and pull back f, then this can be written as f and in fact, if I'll just write it as a theorem, and this is Taylor series. If I write the up to the kth term, so it's basically a Taylor approximation. So you can literally view this as, you can literally say that the pullback of the function f is the exponential of t times the vector field applied to f. Okay, that's the advantage of thinking of these flows in terms of how they affect functions. It's really an exponential of the differentiation. It's kind of cool that if you give me a vector field, right, and if you put it into the exponential formula, you exponentiate the vector field, what it produces is a flow of the vector field. It produces a motion. So you can really see that this is the infinitesimal motion or infinitesimal symmetry, and this is the actual motion. actual symmetry. Okay, so I don't want to say any more really about vector fields than what I've said. The basic idea is that if we simply rephrase what you learned in ODEs, what we see is that a vector valued function, a vector field, can be integrated to a flow, and this flow can be thought of as acting on points, or it could be seen as acting on functions, and it's the same thing. It's just a different point of view on the same thing. So okay, so far I've just told you only the very minimum about the Hamiltonian formalism, but the minimum thing is that there is a vector field, and so we do need to flow it, and so you need to know something about how vector fields can be integrated. Okay, we're going to take a break. Can I take that question? Someone had a question, but it's gone down now.
Oh, hey, yeah.
Hi.
Hey. I was just the last thing we were talking about tangent vectors acting on functions.
Yes.
And so we're taking functions from C infinity from M to R back into itself.
Yeah.
I'm kind of accustomed to thinking of these tangent vectors as defined at a particular point. So like you might have like d by dxi or something at a given point P in M or something like that. Is that how are we working with it differently here when we're using the flow map?
Yeah. So this is the key thing. So here we have
Okay.
the unit vectors, right? But the coordinate, the coefficients, they depend on position. So the vector will be moving around depending on where you are, right?
Okay, perfect.
So that's why it's so sensitive to the initial condition, that if you are at one point, the trajectory will look one way, but if you're at a different point, it will look different. But the important thing is that no matter where you start, you're going to get infinitely many trajectories that are all independent, which are all staying away from each other, and you just get this kind of flow of a fluid, right? And the flow is not uniform in any sense. The only thing that's uniform is the flow of time, that you have to, every point flows for a certain amount of time, and they can all land in a different location, and you get this map.
Mm-hmm.
You see, like all of the points are flowed, and they're all flowed in different directions depending on the value of the vector field at that point. That's part of the nonlinearity of the problem, right? Is that as you move your initial condition around, the resulting location might be crazily different, right? It might be very, very different depending on where you started, and they will not vary linearly in any kind of predictable way.
Cool.
Any question before we break? So I'll do when we come back from the break, I'll do a simple example of this flow and then tell you the rest of the Hamiltonian formalism. Okay, let's come back in 10 minutes, 3:25.
Can you scroll up just a little bit so we can see the last thing you wrote? Thank you.
Okay. Okay, so let's do the first example where we'll see a flow happening. This is in the harmonic oscillator. So let's let's set everything up slowly. So we have a configuration space. Which is the simple space R. It has a coordinate X. And we have a particle with mass m, a positive real number, which is positioned at some point in the real line. And we're going to, at 0, we're going to put a spring and attach it to m, so that m will move side to side under the influence of a force. The force should be a vector field on the configuration space. And that will be just minus kx for some k positive, which is called the spring constant. And the fact that the force of a spring is like this is called Hooke's law. So this means that if the mass is positioned at 0, there is no force. But the further the mass is from the origin, the greater will the force be, and it will be pointing towards the origin. So the force is kind of, if I draw the force vector field, it would look like this. It's very small here. It's growing, and it's pointing this way. Okay, the further that you are, the greater the force field is, and it's always pointing towards the origin. Okay, now what we want is to introduce the momentum variable, P. So we're going to the first order formalism. So that's another real variable. And so now we get phase space. The phase space is R2, and it has X and P together. So we've doubled the space. We have position and we have momentum. Okay, and our vector field, the Hamiltonian vector field, remember that the Hamiltonian vector field was like this. So the X component is M inverse P, and the P component of the vector field is F of X. So we've got the X component is the value of P divided by M, and the p component is the original force field, so minus kx. Okay, so if we were to put m and k to be equal to 1, then this vector field would look like this. It would be p minus x. So at any point, the x component would be the p component, so it would be like this, and the p component would be minus the value of x. So it would be pointing this way here. And you can check that it's pointing like this. And the size of it depends on, it's linear in x and p. So if x and p are small, then the vector field is small. And it's pointing in a circle like this. And we have a fixed point at x and p equals 0. At the origin of the phase space, we get a fixed point of the vector field. Is that okay? Does everyone see what I'm saying here? So now we need to find the integral curves. So just in terms of the flow of information, we started with this. This is the Newtonian setup. And then we went to the Hamiltonian formalism. That didn't involve introducing any new information. We didn't need any additional information. We just went from second order to first order. And now, given all this, given the setup, we need to solve, which is to find the integral curves or the flow of the Hamiltonian vector field. Okay, so in this case, it's easy because the vector field is linear. Look at the components of v. You can see that it depends linearly on the coordinates. Okay, so what? So if we yeah, so if we want, we can write this vector field in terms of its coordinates as a vector. So it's m inverse p minus kx. And we can write this as a matrix acting on x and p. And if k and m were equal to 1, this would just be 0, 1, minus 1, 0. Which this matrix 0, 1, minus 1, 0, that's just the rotation by 90 degrees operator. Okay, so let's call this A, this matrix, and what we have is xp d by dt is equal to A xp. So the Hamilton's equations are given by this. I'm just writing it now as a matrix vector type equation where A is constant. So the fact that I can do this is all because the vector field is linear. I can write it as a linear transformation. Of course, normally I wouldn't be able to do that. So shortly we're going to see an example which is not linear. Okay, and such equations are really easy to solve. It's basically y prime is equal to a constant times y. So what's the solution to this? How do you solve y prime as constant times y?
E to the A, e to the matrix A. So it's a matrix exponential times xp.
E to the A times xp. But where is the variable that the equation is in terms of, right? We have y prime dy by dx, or there's a certain independent variable that should occur in the solution, because it's a differential equation where we take derivatives in time. So time should appear in the solution.
Is it e to the TA?
Yeah, the solution to y prime is equal to cy is e to the cx, right? So this should be, it should be e to the t times the constant in front, okay, times x, whatever the initial value is. That would be the solution.
Professor?
Yeah.
This also sort of resonates with the earlier exponential of the vector field thing.
Yeah. Before we were talking about the exponential of a vector field. Here we're talking about exponential of a matrix, but the matrix is coming from a linear vector field. So it's the same reason. It's the same equation. So whether you represent your data as a function, as a matrix, as an operator, it's the same equation, so the solution will always be the same. Now, okay, so let's try to solve this even more explicitly. So what I'll do is I'll just investigate a little bit this matrix A. So the way that the standard algorithmic way that you would produce this matrix exponential is that you would diagonalize the matrix, and then now that you have it as a diagonal matrix, you could just exponentiate it. So this is how you could approach this problem. I'm going to do it in a slightly different way. I'm just going to investigate what is the square of A. If this is just a kind of observation, it's not the standard way of solving it. So you just look at the fact that A squared is what? Well, you would get minus m inverse k, 0, 0, and then minus m inverse k. So what you would get is minus m inverse k times the identity. Okay. So this minus k, the way they always write it is k over m. This minus k over m thing, this is a positive number. And let's write it as omega squared. I'm just defining a quantity omega, which we'll interpret later. And because of this, I can put the omega into the A. So I can consider, for example, omega inverse A. If I square that, then I'm going to get A squared over omega squared, and I'll get minus 1. Why do I do this? Just because I love things that square to minus 1. I just love it. And that's my favorite thing, is to have something that squares to minus 1. Because then it's like the number I squared is minus 1. Okay. And I also love, we know that we have this formula cos t plus I sine t. Whenever I have something that squares to minus 1, this equation holds. So let's do it. So then we have e to the ta. This is e to the t omega times omega inverse A is equal to e to the t omega times something that squares to minus 1. So I just use my formula. So it's cos t omega plus I, plus omega inverse A. Sorry, let me write it down here. Sine t omega, where this thing, oops, that's too big. I've highlighted the thing that squares to -1, my favorite thing of all. So what we have is, so what does this mean? Here, this means here, this should be the identity, because here secretly there's a number 1. So so in other words, if I write this out, I'll have if I write out, let's say, the solution e to the ta applied to x0, p0, then what I'll get is x0 cos t omega, p0 cos t omega, plus sine, x0 sine t omega, p0 cos t omega. And so if you write that out, you'll get x0 cos t omega. And then what is omega inverse A? It's just a constant multiple of A. A was this off-diagonal matrix, which had, so you'll get A has an M inverse acting on the P. So you'll get omega inverse M inverse P0 cos t omega. And then here you'll get P0 cos t omega plus omega inverse with a minus k. So minus k x0 sine t omega. Okay, but okay, so if I just to draw a nicer picture, let's assume that m and k are equal to 1, and then omega would be 1, and this would just look like x0 cos t plus p0. Oh, sorry, what did I? Oh, see what I did? I put I switched here, cos and sine. Oh, wow, look what I did. I can't believe it. Look, this is nonsense. They're both cos. So, oh, wait, no. Oh, yeah, sorry. So this is, what did I do wrong? Here, this is the part that's wrong. Sine. Yeah. And if you want maybe to write it in a more kind of common way, we could take this and move it in front. Okay. So if I put m and k is equal to 1, so that omega would be 1, this would be x0 cos t plus p0 sine t, and minus x0 sine t plus p0 cos t. Okay, and no surprise, what you are getting is, if x0 or p0 is some point, you're getting just a rotation into a circle like that. And depending on where you are, you will be on a different circle But the interesting thing is that the speed at which the angular velocity is fixed, no matter how far out you are, that's it's the same rotational speed, cos omega t, and the speed of the rotation, or the frequency, is omega, and that's why we call it. I mean, that's the typical letter to be used for frequency is omega. So omega, which is the square root of k over m. So let's make some observations about this. Independent of the initial condition, the motion is rotation in phase space with fixed frequency omega, which is the square root of k over m. So if you have a stronger spring, the spring constant increases and the frequency increases. And if the mass increases, the frequency decreases. If you scale the spring and the mass at the same rate, it will not change anything. So you can see that there's a proportionality between the spring constant and the mass. Anyway, this is all So, okay, but so in phase space, that's how it moves, but that's not what you're interested in. You want to know in configuration space, how does the actual mass move? Well, this is the great thing, is that the second component is totally irrelevant in a way. You don't really care about how the momentum is changing. That's interesting to know, but what you really wanted to know is how the position changes. And what you can see is that it's exactly by these sine and cos. So in other words, it's just going back and forth at a certain frequency. So if we project, so okay, let me phrase this. So finally, to find the actual motion x of t, all we need to do is project from the phase space to configuration space, and what we get is just x of t is right. And so we just get, if we graphed it in time, you would just get simple harmonic oscillation. In other words, it would make a note. And so maybe it's funny to call it harmonic if there's not more than one note, but anyway, there's one frequency. Okay. And the period would be, how much time does it take to traverse one full revolution? It would just be 2 pi divided by the frequency. So, okay, so it's a complete solution to this very simple problem. So what you see is that there are multiple solutions, right? There is a solution for any initial condition. The solution is defined for all time. The flow is just rotation of the plane of phase space. And here I want to make one important observation, which is that when you look at this trajectory, when you look at these trajectories, the position and the momentum are changing with respect to time, right? Everything is changing, but there is something that is not changing. What is that? you can just by inspection, you can see that there is a certain characteristic which is not changing with respect to time. What is that?
Amplitude?
What do you mean by amplitude?
The
What is the
distance,
amplitude here?
the peak and the valley of the waves, the distance between the peak and the valley.
Okay, but
shrink.
so you're right, but I want to phrase it in an even more obvious way. When you look at the motion of these particles here, what is not changing?
So root x squared plus b squared?
Which is normally known as what?
The radius of the trajectory.
The radius of the trajectory is fixed. So the radius is a conserved quantity of the motion. And it can be anything from 0 to infinity. Okay, the radius is a conserved quantity. And so another way of saying this is that there is a function, there is a function on phase space, namely x squared plus p squared. Actually, it's if we include the k and the m, it's this combination. It's x squared p squared. This function is preserved by the flow. So in other words, if you know the initial value of this quantity will remain unchanged in the future. So it is a conserved thing, and it is known as the total energy. Okay, if you look at this total energy, you see two things. You see there's this term here, which comes from the spring, and you see this term here, which comes from the speed, the velocity. This is called kinetic energy, and this is called potential energy. Neither one of them is a conserved quantity, but the total sum is a conserved quantity. Okay, so yeah, you can kind of stare at phase space and you can see this conserved quantity.
Sorry, what's the word just about radius? The HO, so like something is just the rotation of phase space. Like I don't.
The flow.
Oh,
the flow, phi t v, is rotation of phase space. That's what the flow is doing. Okay, now, okay, so there's not much time left, but let me try to explain. I won't try to cram it all in today, but let me explain something important. So what we did was we started with the Newtonian point of view. We got a force. We turned the force into a vector field on phase space. We solved the flow. We projected it out to find the change in x. And then by looking at phase space, we kind of noticed that there is a conserved quantity. We also noticed that there is there's a symmetry. And we have a conserved quantity. So we have here a symmetry, and we have here a conserved quantity. So it's not a coincidence that both of these things are happening. It's a part of a general idea. So the Hamiltonian formalism was designed, or was it discovered, and is useful mainly because it simplifies the flow of information in the following way. So with the Hamiltonian formalism, we can kind of reverse the flow of information. It turns out that in the Hamiltonian formalism, you do not need to start with the force field to create the vector field, and then solve for the flow and find the conserved quantity. You can go backwards. You start with a function on phase space, and that function generates all the rest of the information. It generates the vector field, and the vector field will automatically conserve the function you started with. So the purpose of the Hamiltonian so in the Hamiltonian formalism, we need not start with V, but rather just a function hxp. You can choose the function. Any function will do. This function generates a vector field x sub h, which is called the Hamiltonian vector field. And that's the same as the V that we've been studying. And this vector field automatically preserves this function so that hxp is the total energy of the motion. That's number one. Okay, so we're going to see that next week. I was hoping to do it today, but I needed a little bit more time. Okay, and number two, the system may have other motions, not the motion in time, but what I mean is not the progress with respect to time, but it could have other symmetries. Like, for example, if you have a sphere, if you're trying to describe the motion of a sphere floating in space, let's say, then that sphere has rotational symmetry. That rotational symmetry you can also think of as a flow. That flow you could think of as being generated by a vector field. So these symmetries are flows coming from vector fields. So let's say that we have a symmetry. This symmetry comes from some vector field. And this vector field can be generated, just as before, coming from a function. Some other function, let's say k of x and p. And this function will be preserved automatically by the symmetry. Okay, so what I'm saying here is that in order to solve for the time evolution of the system, we think of that time evolution as being a flow generated by a vector field. That flow is generated by a vector field, and that vector field, it turns out, will preserve a function known as the total energy. But it turns out that the total energy actually determines the vector field. It's not obvious, but we'll explain later that if you know the energy function, namely this 1/2 kx squared plus 1/2 m inverse p squared, that function, I can use it to produce the vector field. And that vector field will generate a flow that preserves the energy, okay? But the cool thing is that any kind of symmetry can be so generated. So if it has a rotational symmetry or a translational symmetry, those symmetries are flows. They will be generated by vector fields, and those vector fields will be determined by a function. Those functions are other conserved quantities. They are whatever else is conserved, other conserved quantities, or momenta sometimes. It's kind of a bad notation, bad terminology, because we're working in phase space where there are already momenta. But anyway, sometimes you say there's energy conservation, momentum conservation, angular momentum conservation, the X, Y, Z components. All of these things that could be conserved, they are functions on phase space. These functions generate vector fields. The vector fields generate flows. The flows are the symmetry that you're talking about, and that symmetry will conserve the function. So this is the system of Hamilton. This is the Hamiltonian system. Time evolution is just one of the possible flows that you could have. And all these flows and all these symmetries are treated on an equal footing. Energy happens to be the function that generates time evolution. But there are other functions that generate other evolutions, other flows, which are not related to time, but rather to something else. Okay, so we're going to do all that next week. Have a good weekend. If there's any quick questions, I'll stick around for 5 minutes.
May I ask really quickly, are those, besides being live, are those courses recorded?
Let me just make sure here. It should be, but I'm worried that maybe... Yeah. Do you not see a link to the YouTube stream?
Yeah, but that's a live stream. Is it going to be uploaded to your account so I can access it later?
Oh, I think so, yeah.
As the video upload,
always does that. I think it always keeps the stream.
Oh.
Yeah.
Okay, good to know. Good to know. Thank you.
You're welcome.
Professor?
Yeah.
Going back to someone in the middle of the lecture, I was trying to think of an analogy of how the flows, like a physical analogy of how the flows affect how the vector field affects the flow. And yeah. I was wondering if it would be appropriate to think of it as like analogous to how we can predict the path of a particle if it goes like through an area of space without any electric field, for example. But if you turn on the electric field, then that electric field will influence the path of the particle takes.
Sorry, try to focus on what exactly is it that you're trying to understand? Is it the action on points rather than on functions, like comparing the action on functions to the action on points? Is that what you're? Which issue is it that you're trying to understand? The way that the flow affects the functions or the points?
The way the flow affects the functions.
Yeah. It's like, for example, if you're trying to study the wind, okay, what you could do is you could say, you could do it in two different ways. Okay, you could release 1,000 balloons, and you could look at and you could use GPS to figure out their positions with respect to time, and then you're going to get the position as a function of time of a parcel of air. Okay, the other way that you could do it is that you could have ground stations all over the planet which are measuring the airspeed. and the motion of the air locally, right? And so what would they be doing? There would be a function on the Earth, which is called, the airspeed, and we would be monitoring this function and how it changes with respect to time. Right? That's the difference. The difference is, looking at just the motion of a point, or looking at how the temperature is changing, for example. Or another way of thinking of it is that you can, if you if you're trying to put on a sweater, right, there's two ways to do it. You could either grab the sweater and put it on, or you could hold the sweater up and then take the child and just inject the child into the sweater. Those are the differences. You can either look at the motion of the person, or you could look at the function on how the sweater is moving across the skin. They're dual. They're kind of it's like a relative motion, right? Which one is fixed? In one case, the particle is moving. In the other case, the particles are fixed, but it's the functions that are moving.
Ah, right. All right, that makes sense. Thank you, Professor.
Hey, I have a question about tutorials. I have a class at the same time as tutorials. I'm just wondering if your tutorials will be recorded and uploaded as well, or if it's just the class.
So the tutorial is. Can someone tell me when the tutorial is?
It's right after class. I think it's from 2 to 3 on Wednesdays. Is that all right?
Is that correct?
Like your office hours, I guess.
Pretty sure that's what
at the same time as office hours?
No, sorry. By tutorial, I meant your office hours.
Oh.
So my bad.
Oh, okay. So, well, I was not intending to record the office hours, but I think we could do that if. Yeah, I'll try. I probably will just forget to turn off the recording. I mean, I don't know. The reason is that we're not necessarily supposed to have the office hours recorded, because people should be able to ask whatever they want, So I
see.
We'll see if there's something that if there's something important being discussed, then I'll try to record it. But yeah.
Is there other times where I could ask you questions about the class?
Well, we could have we're going to have some kind of a not a piazza, but maybe we'll have some kind of an online discussion thing that you can ask questions, so that you can get to know each other if you don't already. And so you could ask questions there.
Okay.
If anyone has a suggestion, you could let me know. I mean, I think piazza is too annoying for a class this size. This is a pretty small class. We could do something like, does anyone have a suggestion? Anything you prefer? We could do a Slack. I'll send a Slack invite next time.
Okay. Thank you very much.
Okay. All right, everyone. Have a good weekend. Don't get COVID. See you later.
Professor?
Hi.
I was wondering if I could ask a really, really quick question.
Yeah, go ahead.
You said about that you can generate a flow, a vector field using a function like the invariant function for energy. We didn't go over exactly how that generating works, right?
Yeah, correct.
And we'll go over it later.
Yeah, next week.
Okay.